Hi, welcome. This is Brian from Denso, Germany, participating in the EU Horizon 2020 FOCETA project and leading the use case of continuous engineering for safe and secure intelligent automated valet parking. In this video, I will demonstrate a subset of our use case results with running tools regarding safety assurance for an AVP system in simulation. When considering safety assurance for AVP, we start with identifying the most relevant scenarios in a parking environment and their associated safety goals. In this demonstration, let's focus on one example, which is pedestrian crossing with potential occlusion. And the goal here is to ensure that within an operational design domain, ODD, which is essentially a constraint input domain, the eco vehicle should have no collision unless it has a zero velocity. To be more specific, the scenario involves two pedestrians at risk. The first pedestrian walks out from the parking slot and stops at the side. The second pedestrian also comes out from the parking slot but keeps crossing the driveway, being potentially occluded by the first pedestrian from the angle of the eco vehicle, which is now automated and driven along the highlighted path approximately towards a designated stop. Meanwhile, the environment conditions may change during operations, bringing us to the more detailed ODD attributes below. Essentially, for the design and testing of the system, we concretize the scenario setting with 7 attributes, including the type, velocity, and start time of the second pedestrian, the eco velocity gain, and conditions such as precipitation, visibility, and illumination. This will be the domain around which we would like to assure the safety of the AVP system. Now with the problem set up, I will go into 3 parts of our demonstration. The first part shows the system under test in simulation, which is supported by FOCETA requirements engineering and system modeling techniques. The second part tackles safety assurance within the ODD using a search-based testing framework and runtime monitoring and enforcement techniques. And finally, the third part illustrates how the runtime measures may be extended into out-of-ODD cases. First, the system under test simulation. In our use case, the system under test contains the environment and sensors, the eco vehicle's sensing, planning, and controlling functions, as well as a vehicle dynamics model. All of them are modeled and simulated in MATLAB Simulink in conjunction with other tools including Prescan, ROS, PyTorch, and Functional Mockup Interface (FMI). As mentioned, throughout an operation, the eco vehicle will follow a given path from a global path planner, and at every time step, it will obtain a camera image to perform 3D object detection and take an emergency brake if necessary. Let me show it in action now. First, I'll bring up the scenario designed in the graphical user interface of the Prescan simulator. I'll open a so-called experiment file prepared for the scenario. So we see now the scenario with a map of the car park, the automated eco vehicle with a camera sensor, and other road users with predefined trajectories including the 2 pedestrians of interest. I've also attached a world viewer in the scenario for inspection later. Here is a clearer view on the scenario design without the sensor beams. Now to simulate the scenario with the automated vehicle's driving functions, we invoke the Simulink run mode, bringing us to the MATLAB interface, where we can further open the so-called Simulink compilation sheet. Here we can see the actors designed in the simulator, including our automated vehicle. And if we click on it, we'll see its functional components, including the camera sensor, 3D object detector, planner and controller, emergency brake, and vehicle dynamics. Now let me run the simulation. And after some compilation time, we'll see the simulation running. In this case, the eagle vehicle detects the crossing pedestrian and triggers the emergency brake in time. So I hope this gives the taste of the system under test in simulation, and we'll proceed with assuring its safety within the defined ODD. For safety assurance within the ODD, I'll first talk about design time testing and then runtime monitoring. In our use case, we employ a Python-based framework OpenSVT developed in FOCETA. Recall that we have the scenario setting and the 7-dimension ODD as well as the system under test. The strategy we are taking here is to define an objective function and use an optimization algorithm to find critical scenarios more efficiently. Two examples of objective functions are given on the right. First, we can minimize the closest distance between the eagle vehicle and the second pedestrian and maximize the eagle velocity at this point, searching for critical scenarios with large impacts. Alternatively, we can also formalize signal temporal logic specifications such as the following. If the distance to a pedestrian is below a threshold, the eagle velocity should be 0. The specification can be evaluated with another tool, RT-AMT, to give a quantitative robustness indicator of the system under test, and we want to minimize this indicator to get critical scenarios. Let me show how it works. Here we are seeing the same scenario set up in pre-scan, except that the world viewer is changed to a camera on the eagle vehicle for clearer illustration. And again, we see the compilation sheet showing the eagle vehicle which contains the functional components. Now, to conduct automated testing with the Python-based OpenSVT framework, we will share some MATLAB controls with the Python environment. And then we can go to our IDE containing the framework. We can see here the file that defines the scenario path, the ODD search space, the objective function, and the optimizer. Now I will trigger the testing process. And we will see the Python-based framework is communicating with MATLAB and creating a scenario with certain attributes. With the visualization, we will see that the testing framework has created a slightly foggy scenario. And in this case, the eagle vehicle managed to avoid a collision. This testing is an iterative process, so we can see the testing framework continues with the second scenario. And in this case, it is a scenario with much more adverse environmental conditions. And our eagle vehicle bumps into the crossing pedestrian this time. So typically, the testing process runs for a certain budget such as time or iteration constraints, and one can analyze the final outcomes to identify where the system under test fails and repair it accordingly. In this demonstration, however, we will not dive into that direction. Instead, we will show another branch of our results, namely runtime monitoring. In the use case, we've designed a perception monitor that infers risk values from the input and output of the object detector, and feed the risk values to a safety shield which sends certified commands back to the original system under test. Notably, the perception monitor is implemented with the PyTorch deep learning library and contained in a ROS node, so we use MATLAB ROS bridges to transmit the signals. To show the effect of the runtime monitors, I will replay the critical scenario that was generated by the testing framework just now. First, let me come to the MATLAB Simulink environment and activate the ROS bridges and the safety shield. This is done with some switches that we implemented in an initialization script. So we can see them activated now. I'm also bringing up some scopes for inspection later. Lastly, let me go to the ROS environment to start the perception monitor ROS node. Once it starts to run and standby, we see the node is subscribing to the input and output of the object detector and publishing risk values. Now I'll come back and run the simulation. As we can see, in the originally critical scenario, the runtime monitors are now predicting risk values and taking the certified commands in blue to decelerate the ego vehicle and avoid the collision. This shows the effect of the runtime monitors within the ODD. Now, in the next part of the demonstration, I will show their effect even in out-of-ODD scenarios. That is, to consider safety assurance out of the ODD. To create out-of-ODD scenarios mimicking the ever-changing world, we replace the second pedestrian with novel objects that are not seen by the ego vehicle before. These cases will not be covered by the automated testing framework that we just saw. For instance, I have assigned a cow here, and we can also see it in the compilation sheet. Just to show, we have the same system under test with the runtime monitors activated, and now I will run the simulation. We can see that even in such a out-of-ODD scenario, the runtime monitors are reacting to the unseen object and slowing down the car, while the original baseline system under test would have taken the uncertified acceleration commands and made a collision. In conclusion, with FOCETA project results such as critical test case generation and runtime monitoring enforcement, we are one step closer to assuring the AVP system safety inside and out of a wide ODD. Thank you very much for your attention, and I hope you enjoyed the demonstration.